Okay, so we are getting closer and closer to statistics thing. And then the basic statistics concerns, at least this module concerns of two things. One is the estimation, and we'll talk about point estimation, which is, for our situations, we only consider estimating the mean and also estimating the variance of the populations. There are other things. Okay, thank you. There are other things, of course, that we want to estimate. After all, the whole idea of estimation is we wanted to know about the populations, and we do it by a small sample. Small depends on two things. One is the heterogeneity of the situations. Suppose if everyone is at the same height, then all I need is just measure one guy, and I will be able to find out the average height or the height of the entire population. But if the population is getting more and more is getting more and more heterogeneous, meaning that the variations in our case is the sigma or sigma square is large, then of course we have to sample more. So this would be something that we just tell you about reasonable, what we call estimators of providing point estimations of the population mean and also the population variance or population standard deviation, because they differ by a square root. And another area would be interval estimations. That would be we'll talk about confidence interval for the standard for the mean of the population, and also for the variance or the standard deviation of the populations. We do not want to have just a number to estimate the unknown parameter in the population, but we want to give an interval with a good possibility of capturing the unknown parameter. We will make precise a bit later. This is an example of where we can actually write down the actual distribution of the X bar, the sample mean, if you pick 2, and your population has only 5 possible values. And so this is an exhaustive way of listing out the whole thing. And then we have this. Now we will come to this a bit later, all right? It is a general result. The mean of the sample mean is equal to the population mean, and then the variance of the sample mean is n-fold less of the variance of the populations. So basically, if you have a distribution, and if you pick one, it is you don't expect to hit at the mean. So you will say, let's say we overestimate the mean of the population. But then when you take another measurement from another sample value, it is likely to be underestimate. And so so when you do let's say 10 sample size, chances are about 5 or 6 or 4 would be overestimate, and then the others will be underestimate. And so taking the average of all this cancel out the underestimate as well as the overestimate. So as a result, it is sharper, all right? And this is reflected by these expressions divided by n, because the variation actually shrink by n times, all right? So that is the merit of having a larger sample size, and something that I mentioned earlier, depending on how heterogeneous is your population. Because if your sigma x square here, the numerator is big, then in order to have a sharp interval, then of course you have to have a larger n. But if your numerator is small, you don't need to have a very large n to achieve the same accuracy. Okay, so that is the situations. And we have shown, okay, this is the result. The mean of this is equal to this, and then the variance of this is this. Let's see whether we prove it. We didn't. And there is a typo here. We have to change it to epsilon strictly positive for the statement. Because let's say the statement would not be right when, say, epsilon equal to -1. If epsilon is equal to -1, this statement will always be true because the absolute value will be bigger than -1. So as a result, the probability will always be 1. So it can't shrink to 0 no matter how large your n is. So there is quite a serious typo. So we have to say epsilon is positive. So this is what we actually call, if you Google it, this is usually be more specific. It's called weak law of large number because there is a stronger law of this. So it is just saying that when your sample size is larger and larger, the event that your sample mean differs from the target mean exceeds a certain tolerance level, say let's say 0.1, then this is getting smaller and smaller, this event, the likelihood, if your sample size is larger and larger. Now the result of this is actually due to Chebyshev, and the Chebyshev inequality is actually used here in a very straightforward manner. We are not going to prove this, even though the proof is just a few lines. But the more important thing is this says that as the sample size increases, the probability that the sample mean differs from the population means goes to 0. So this is the main message of the previous slide. Another way of looking at this is that it is increasing likely that the sample mean is getting closer and closer to the population mean. Now remember that the mean mu is something that it is not known to us, is the population, and this is something that we are interested to find out. And to find out here, what we do is we collect samples. What it is corresponding is we just based on our empirical evidence, so to speak, our experience or our empirical experience help us to invest to know something that is unknown to us. All right. So that is the relationship between empirical evidence and something that you want to know, and that is the mean mu. So this is an example. This is just now here I have a uniform distribution, and so we work it out, and so I think we did that, and so this probability is actually not very big. It's about 3%. If you have such a large sample size, the sample size here is this is 3 million. Of course, it is. Rather, it's really, really huge by any means of judgment. But if you are doing it in the computer, this is not too big. It probably takes just split second to do that. Okay, the central limit theorem. We mentioned the importance of the central limit theorem. It says that basically it explains why the normal distribution appears everywhere. It says that if you have a sample x1 up to xn with mean mu and finite variance sigma squared, we do not assume any further we do not make any further assumptions on the distribution of the populations. All we assume is that the population has a finite mean mu and has a finite variance sigma square. Now, of course, you might think that this condition is rather redundant because all your experience is the mean and the variance are finite. Now, mathematically, there are many distributions that don't have a finite variance, have a finite mean mu, and also not even finite mean mu. But of course, if you are dealing with data, I think it is almost satisfied. All right. The sampling distribution of the mean xn bar. So we are not talking about any other thing. We are talking about the sample mean. All right, which is the average of this. Okay. And here we have to divide by sigma over square root n. This is our, it is because of the previous slides. The variance of the sample mean is 1 over n times the variance of x. So when you look at the standard deviation of x bar, this is the standard deviation of the population over square root n. That is where the square root n comes from. All right, and here, this is, okay, the mean is always 0, and the variance is always equal to 1 because of the way we standardize it. The importance of this statement is saying that this is normal. So this little n here is the crux of the whole statement, saying that the distribution here is closer and closer to being normal, all right, normally distributed. So if we recover this, then the mean of xn bar is, the sample mean is almost like mu, and then the variance is sigma squared over n, and so we are just rescaling the things up, okay, by we rescale it, and so we have a sigma squared over n because we square this for this part, and then we move the origin originally from 0 by mu unit. So as a result, I have a mu here. So we are describing the sample mean in this manner. All right. So this is when n is sufficiently large. Of course, the thing is how large is large. All right. So no one actually have a very, something like a rule of thumb for many other distributions. Because when you have a rule of thumb for something very general, there is a trade-off. If you want it to be very general, then your sufficiently large would be very large in order to cover more cases. But if you look at specific situations, it can be small, all right? So here the rule of thumb is saying that n is bigger than or equal to 30. I think we have covered this. So again, don't take it too dogmatically because it is just a guideline. All right. The whole thing is ask yourself this: is the distribution of the population likely to be symmetric about the mean? If it is the case, then you don't actually need a very large number of sample size. If it is very skewed, like the later slides, then you will need a larger sample size to correct the skewness because the normal distribution is symmetric. Okay, so this is the thing that we talk about. I think the lecture note did not explain very clearly. Now the sample size is n equal to 2, so you pick any two numbers here and then divide by 2, so you will get a sample mean. And after that, you repeat these procedures many times. The lecture note did not say how many times they do it. For example, around here is about 200 times. And so 300, right? So if you add up all of them, definitely it might be around 10,000. So I'm not sure how many times they repeat it. So basically, what they do is, for one iterations, they pick any 2 points randomly from this distribution, which is very symmetric, and then average it, so you get a number. You repeat these things, say 10,000 times, and now you plot the histogram of this 10,000 averages that you have done. And here, this is the other situations. You pick sample size of 5, meaning that in one iterations, you pick any 5 numbers here at random, and then you find the average, and then you do it, say, 10,000 times, all right? And here, you pick 30 numbers and take the average and do it 10,000 times and do the histogram. So you do it the same for all of these 9 histograms, except that this is size, the sample size is 2. This is also sample size 2, but this is distribution is highly anti-symmetry, all right? And this is very symmetrical as well, and here. And you will see even when the sample size, even for n equal to 5, in the first case and the third case, they look closer and closer to a bell shape. So the rule of thumb for 30 is definitely fairly, sufficient enough, all right? And here, even for n equal to, but you can see when the underlying population is not symmetrical, it takes a while for the symmetry to achieve, all right? So this is, at the beginning, it's very skewed. Basically dropping like this. And when you do it for 2, you correct a little bit, because most of the time you collect something here, and then with some probability here. And so when you take the average, it is around here, all right? And with some probability, you pick 2 points on this side. And so as a result, you also have, something like this. Okay. So this is where the usefulness of approximations. I think we have done this. All right. Now, if you are willing to assume 16 is large enough, then you don't need to assume at the beginning that each of the light bulb is approximately normally distributed, because if you assume 16 is large enough, then you are basically using the central limit theorem. But if you think that 16 is not quite enough, then you need to make this assumption here, all right? Now, of course, I think for students, one obvious question is when is it feasible to assume? Unfortunately, the decision is usually from us. So, but when you're working, as long as you know what you are assuming, doing it. Now, of course, subject to whether you feel that your assumption is reasonable, then you can assume it. If you feel uncomfortable about your assumption, then you should use it with caution. Okay, anyway, after this, then this is just, we will have this, all right? And so I think the basic things that you need to pay attention to this example is the mean of the X bar is still the same mean as the population, which is 800, but the variance is being 16 times less. All right, so so you divide by 16. This is basically the only thing in this example. And after this, because of X bar here, you can calculate this. This is assuming you are using the statistical table. If not, if you are using either Excel or the R, you can basically do it here, all right? You don't need to do this standardization. Okay, now X bar denotes the mean of a random sample of size n from a uniform distribution. Now, this is exactly this graph is here, all right? And then now it is 75, so much bigger than 30. So you will know that it's going to be, the normal approximation is actually very nice, all right? It's quite accurate. So we are applying the central limit theorem as before. So this is the most important thing in all your subsequent calculations, is to identify, this is from central limit theorem, approximately normal, all right? And then the mean will be just 1/2, and then the variance will be the population variance, which is 1/12 from the uniform distribution, divided by your sample size. Okay, this is it. So this example is very repetitive of the previous one, except the only change is to change the mean and the variance. Now, the merit of this central limit theorem now is just reduce everything to computing the population mean and also the population variance, okay? And of course, you have to adjust it by dividing the sample size. So the calculation is very routine. The only things that you need to do is to calculate the mean and the variance, all right? Okay. Again, the Poisson with parameter lambda. And since this is the sample size is about 50, it's 50. So let's assume it is okay. All right. And so we will have this, all right, as a normal distribution. And then this is the variance, because the underlying population is Poisson. So the mean and the variance are the same. So so this is this statement. This statement is very quick, but it involves the knowledge of the Poisson property. All right. And once you have this, then again, it would be just a repeat of what we do. And so, of course, to be more precise, you might want to add the word approximately. So that is why we have okay. Now, strictly speaking, this is not an approximate sign. This would be an exactly equal sign, because S50 is coming from sum of Poisson, right? The xi's are Poisson, and so Poissons are non-negative integer value. So you are adding up integers, so it will be an integers. Okay, and as a result, if the integer is no smaller than 3, this will be the same as the integer has to be strictly bigger than 2.5. So this is actually a strict equal sign. It's not an approximate sign. Now here we are just doing it by dividing everything by 50. All right, and so we basically simplify my right-hand side. And here I'm doing the standardization. And if you take Z to be the standard normal, the approximation sign should come here. Okay. So and if you're willing to, so let me repeat. This would be a equal sign, and this would be approximation sign. And then here you can take it as equal sign, because it is approximate is because you take this number and round it to be 0.82. But in theory, you can calculate this number more accurately, because it is coming from this. And so the result is about 21%, all right? So this is what the continuity correction is being used. Bowling league, all right? In a bowling league season, bowlers bowl 50 games, and the average score is ranked at the end of the season. Historically, John averages 175 a game with a standard deviation of 30. What is the probability that John will average more than 180 this season? Okay. Basically, this is also typical of statistics. Of course, sometimes people argue about it. Is to predict the performance of a person or something like stock or whatever. You are using the past year. This is what we call historical data. So we are predicting what John will fare this season by looking at how did he do in the previous season. All right. Now, of course, in a lot of situations when things don't change very fast, this historical data might be a good guide for your predictions. But if things does change quite drastically, then it may not. So, but anyway, we were told that the mean of John's average bowling scores is 175, and the standard deviation is 30, and then n is 50. So basically, again, we quote central limit theorem, and we work out the mean and the variance of the sample mean, and which is the population mean. The population mean was taken to be from the last year, and then the sigma square is also from the last season. And but now I'm talking about the average of n games, average of 50 games, so I have to divide by 50 here. All right, so this is this. So with a probability of 43.4%, John may score higher than 180 for the average, all right, for one single game here. Okay. So the nicotine content of a single cigarette of a particular brand is a random variable with mean mu equal to 0.8 microgram and standard deviation 0.1 microgram. If an individual smokes 5 packs, 20 cigarettes per pack or per week, all right? So, so about 100 sticks a week. What is the probability that the total amount of nicotine consumed in a week is at least 82 microgram? So again, we use central limit theorem because we have to use central limit theorem because we were not told the original distribution of the nicotine content in one cigarette, all right? So, but now we are talking about over 100 sticks here, because 5 packs, 1 pack 20, so n is 100, and so we can use the central limit theorem, and so this is it. All right. So xi denote the nicotine content of the ith cigarette that he is smoking, and I runs from 1 up to 100, and so we have this, and so this is it. All right. So if you want to be a little bit more careful, you can write approximately here, and so yeah, all right. So this is about 2.3%, the probability of exceeding 82 microgram. So when a batch of certain chemical product is prepared, the amount of a particular impurity in the batch is a random variable with mean value 4 gram and standard deviation 1.5. And if 50 batches are independently prepared, what is the approximate probability that the sample average amount is between this? So we are just basically, the question is, okay, the question is basically asking for this. And then now we apply central limit theorem, and the central limit theorem asks us to identify the mean and the variance of the population, and which is given by this. And so things are just very repetitive here. Okay. I want to do a little. I want to have a break here, which is good news for you guys. because we are going to start a new topic, and we are going to talk about sampling distributions. And in this chapter, we'll be introducing the distribution. So far, we have introduced the distribution of the sample mean, but sometimes we are interested in the sample variance, and that is where the chi-square distribution comes in. And sometimes we are interested to compare the two population means. I will give you some motivations, some examples. And so we have to, when the sample size is not large and the population variance is not known, which we have to estimate it from the sample variance, there is uncertainty there. And so as a result, the distribution has been changed from the normal back to the t distribution. And so we will talk about the t distribution. And later we will talk about the F distribution, because when we are comparing the sample of two means, one of the assumptions is that the two populations have to have comparable variances. But we have to check that first before we apply the result. So let's have a break, and come back at 10:40. All right. Maybe I have a little statement about why we are interested in the distribution of a lot of sample quantities, the sample mean or the sample standard deviations or the sample variance. Because basically in a lot of decision making, if I do assume certain things and then I calculate the event, and if the probability of the event is small, then actually it is a little bit convoluted in the argument. I assume it this way, and then I assess the situation, and if the probability is small, let's say less than 5%, then I question my assumption, basically. So in your hypothesis testing, this is the kind of approach we do. We assume the null hypothesis is correct, and then we calculate the null hypothesis of, under the null hypothesis, I'm observing this kind of empirical data. Then if the probability of observing such a real data, the empirical data, is less than 5%, we deem it as unlikely. If it is unlikely, then that leads me to question back my null hypothesis assumption. And that is where, the tendency is to reject that. All right? So that is basically the overriding philosophy of doing this. And so one of the important things now would be to know the distribution well enough for the quantity that you are looking at so that you can make a probability statement. Now, if you can't, one way to go would be approximation, if central limit theorem allows you to do so. Or if you if there is some way for you to use your computer to simulate, you might be able to simulate the probability. Now, for example, coming back here, what you will do is to here, suppose your sample size is say 5. Then what you do is now repeat this, say 10,000 times. And now suppose you are interested in assessing whether the distribution of the X bar is bigger than, say, 0.9. Now you look at where your 0.9 is. So 0.9 is somewhere here, all right? And so you ask yourself, what is the probability of getting 0.9 or above? And if you can estimate this probability by looking at the proportion of the time out of your 10,000 simulations that it is bigger than 0.9. And if this probability is very small, small in the sense of 5% or 1%, then you realize that it is unlikely to occur if your underlying assumption is correct. So now you go back and retract your assumption, and that is where you reject your null hypothesis. So the important thing is now I want something like a histogram, all right, of this. Now, of course, if you are able to know the underlying populations, the randomness here, you will be able to do simulations. But if very often we do not know enough, we only know the mean is half and the variance is 1/12. So it may not be like this. It could be some other things. Okay, so you can't quite do simulations in that sense. And there are some, sort of generic statements that enable it, and the central limit theorem is one of these powerful statements. And so this explains why we have to go into detail to talk about other distributions. So now your population distribution, you do not know the shape. All you know is about the mean is 4 from previous experience. And now you do sampling, and now I'm interested to ask myself, the sample mean is lying between 3.5 to 3.8. So this is my interest. I wanted to calculate this. But I have to make some assumptions. Okay, so about the X bar distribution. Here in this diagram, I assume I know the distribution is following this orange curve. And so as a result, if I know this, I will be able to compute the area under this curve for the green region. And so here this is what they do. And in this picture, we are invoking the central limit theorem to say that the curve is like a bell-shaped curve. And so as a result, we can find out the area of the green curve. This step is not quite necessary nowadays because you can use software to compute this probability right away. But in the past, people rely on the table. They need to do one more step to standardize it, all right? So you can actually work out here, okay? Now, of course, to work this out, you have to know the mean of the normal, and also you need to know the variance or the standard deviation of this orange curve, all right? Okay, now we are interested in the difference of two sample means. There are many situations that we are interested in comparing two populations. For example, about teaching methodology, suppose people are interested to compare which one is more effective, say a flipped class or, a traditional lecture and tutorial kind. So they pick, they recruit subjects to, some subjects will go through the flipped class arrangement, and then another set of subjects would be going through the traditional lecture tutorial situations. And then at the end of the, this program, we measured the performance of the students, which group of students are doing it better as a result to trying to understand the difference of the two population means from the difference of the two sample means, all right? So this was just one example. Another example would be something like whether if we want to lose some weight, whether we want to go by diet or go by exercise. So we recruit again we recruit subjects for doing this. One go through the diet plan and then the other go through the exercise plan. Now, of course, there are a lot of complexity in recruiting the people, but let's say everything is done correctly, and the results would be a difference of the two sample means. Many other similar questions, for example, in social science, whether you give out welfare money to the poor, or you enable the poor people to pick up some courses, and so basically some training. So this has been done in many social sociology study, whether it would be good just to give out welfare money versus, less welfare money, but the same amount of money is actually being channeled to, training the poor so that he will be able to find a better job. So this kind of questions pops up everywhere. All right. So we consider the following situations. So basically, we have two populations. One population, I'm going to have a sample, a random sample of size n1 from these populations. Let's say back to the flipped class. So I recruited n1 students to do the flipped class. And then I also recruit n2 students of similar profile to do the traditional lecture tutorial class. So I will have, and then this x1 up to xn1 is the measurement at the end of the program. All right. So in the flipped class, it would be the test score, or this would be the test score after the class. And the two samples are independent. Okay. Now, there are a variety of, this is actually what we call the two sample test. And we assume they are independent. There are other situations that because we want to minimize the individual differences, we usually have a before and after. So suppose you give certain medication to someone, but you are not sure, you might have more than one. Suppose you have two medicines for the same illness. You might want to see, but individual response to the medicines also is a key factor. So one way they do it is actually they apply the medications, one to a person, and then for a period of time, and then do some measurement, and then have a waiting period, which is what we sometimes call washout period. So a period of time where the effect of the medication in the first trial is basically disappear. And then they apply the medicines, the second medications for to the same person, and so we can measure the differences of the effect. Now, to make it even better, they have a randomization of the order of the medication. Some might receive medication 1, and some might receive medication 2, to prevent the order might be also playing a trick there. So here we are. So in that case, the two samples are not independent, because we are coming, X1 and XY1 will be coming from the subject 1, and X2, Y2 will be coming from subject 2, and so on. So this is usually called before and after kind of, and we call it paired sample t-test later on. All right. So anyway, the sampling distribution of the differences of means X bar and Y bar are approximately normal distributed with mean and variance given by this. Okay, here there is a little explanations. All right. Now, let's see. This proof is actually, let me provide a little bit more detail to the proof. So the X bar, which is equal to 1 over n summation k from I from 1 to n1 xi. So I'm interested in taking the expectation. So I'm taking this. Oh, sorry. Okay. Yeah, I was trying to do some animation. So let's try again. So this is our definition. So this is the sample mean. So as a result, you are interested to find out the expectation of this guy. So you take expectation on both sides. And now expectation is linear in the sense that you can take out the factor and then do it term by term. So we have this. Okay. And this is 1 over n summation n1 I from 1 mu 1. All right, because it is the xi's are coming from population 1, so the mean would be mu 1. And now I'm summing this. I have n1 mu 1, or I have a n1 here. All right. So as a result, I have 1 over n1 and n1 mu 1, and so this is mu 1. So this is what the question is. So if you type it, you can cut and paste and recycle the whole thing. Right? And so on and so forth. So, and you will get mu 2 here. All right, in your slide. Now, strictly speaking, the variance of the sample mean has not been taught in our lecture. So, so I will just say something like this. So x1 bar, and I will have the variance of 1 over n, n1 xi. Okay, remember the variance is coming from something like this. Variance of, say, w is equal to w minus the mean of w and a square here, right? So if you if you multiply this one by A unit, it would look like this. And so the A can factor outside the expectation first, and then you can factor the A, and then the A can pull out. So when you pull it out, because it is under the square here, so I will have this. And so it would be A square variance of W. So when you multiply the measurement by a factor, then the variance will be this factor square. All right, and now the factor that you multiply can be negative, but when you pull it out, it would, because of the square, it is the negative factor will the negative part of the factor will disappear. So coming back here, so the factor is n1 and a square here because of the here, and then I'm taking the variance of the sum. Now in a way, the variance is somewhat like a square, so I can expand this out. This would be the variance of the first one plus the variance of the second one. I have an n1 here. The variance of xn1. All right. Now by right, I should have the covariance because how they affect one another. But the covariance is 0 because of independence. All right, because the xi's are independent, so maybe you should memorize this sentence, which if it is easier to memorize than in terms of the formula. Variance of independent sum is the sum of their variances. All right, so variance of a sum is equal to the sum of their variances. So we have this, and now this will be 1 over n1 square. And again, each one will contribute sigma 1 square, and you have n1 of them, so you have this. So as a result, you have sigma 1 square n1. So this is the factor here. And this explains why very often you have a square root of the sample size. Okay. And again, you can copy and paste and change everything to y. All right. So I guess this is probably giving you more details about this. I guess this is rather quickly. All right. And so now we wanted to apply it to x. The minus will be the same. So expectation of the difference. This is because of the expectation. Expectation of a sum, you can always do it term by term. And you think of minus is actually a sum, all right? So you still have this. Now the variance of this, again, you can think of it as x bar plus negative of y bar. So it would be variance of x bar plus the variance of minus 1 times y bar. But the minus 1, when you pull out minus 1 square, so the minus sign will disappear. So that is why you have this. All right. Now this is crucial because there are some occasions that the second term might be bigger than the first term, and if you copy the minus sign over, this term might be negative. But if this is negative, it does not make sense because the variance is always non-negative. All right. So you know. You can't have a negative number. You can't have a minus sign in these expressions. All right? Okay. Now this is crucial because later on, this is being used in the subsequent slide. And later on, when we are doing what we call a pool sampling, we also pool variance. We are going to make use of these situations as well. Okay. So when n1 and n2 are both large, the central limit theorems kick in, and x bar and y bar will both be normally distributed. Now this has not been explained, and it would not be easy to explain. I think it's one of the property of the normal distribution. When you have two normal distributions, the sum or the difference will still be normal, all right? And especially if they are independent, all right? If it is not independent, it is still normal, except that the variance of this guy, the covariance will come out, all right? So we'll probably not talk about this in this module. So, and basically what I'm trying to emphasize is that linear combinations of normal distribution is still normal, all right? And so, so I only have two here in this case. So this is the crux of the whole argument, because then this is just standardization, okay? So once you, so this statement is rather innocent looking, but this is the crux of the whole thing, because if we do not know it is normally, approximately normally distributed, we wouldn't have this, all right? So this actually comes from here, but this is, we are quoting something from normal distribution. Okay, the television picture tubes of manufacturer A have a mean lifetime 6.5, and this and so on. So we are interested in the probability that a random sample of 36 tubes from manufacturer A will have a mean life that is at least 1 year more than this, all right? Now this kind of calculations are of interest. At least suppose you are thinking of whether you are getting the television picture tubes from manufacturer A versus manufacturer B. And of course, manufacturer A has a longer lifetime, but also has more variations. And then manufacturer B has a shorter lifetime, but smaller variations. Of course, this is not in the question itself. Suppose manufacturer B offers slightly better price for the, you are making a television. So, you might be tempted to try to go for manufacturer B, right? Because if it's cheaper. Now, it also depends on how likely that it will last more than 1 year, because you are interested in giving out warranty. So, so some of these considerations, even though this is not part of the question itself, but this kind of things does pop up in real life applications. Okay, anyway, so the subscript A refers to coming from manufacturer A. Subscript B refers to that from the manufacturer B. So we were told that the mean is 6.5, the standard deviation is 0.9, and the number of the sample size that we are testing from manufacturer A is 36. So we have all this number ready. Now, so the mean of the mean of the difference of the two sample means is the corresponding difference of their population mean. All right. So let me repeat. It's a mouthful. This is the difference of the two sample mean, and the mu here stands for the mean of the thing inside. All right. So the mean of the difference of the two sample mean is simply from our from this result, it is just the difference of the two population mean. So we are quoting this. All right. Okay, and this is 0.5, and now we have to adjust the standard deviations because I have 36. So it is the variance from the population 1 from manufacturer A divided by the sample size that I use here, which is 36, and so on. So I work out to be 0.189 as the standard deviation. So as a result, you will have this. Now again, this step is rather unnecessary if you have a graphic calculator or you have some software to do this. So the crux of the whole thing is to calculate the mean of this guy and also the variance of this guy. Okay, that is this is the part that is being tested in a way, and you just need to apply these slides, the results here. All right. So this is where all the calculations is using. Okay, the chi-square distribution. Now, so far we have been talking about the sample mean. There are many situations that I'm interested in the sample variance because the variation might be more important than the sample mean in some situations. For example, if you are making certain instruments, it is not only the mean that is important, but I mean within the specification is also important. So we are interested in estimating the population variance in many ways. All right. So this is a chi-square distribution. Now it turns out chi-square distribution is used in many places. We are not able to do that here, but in a lot of chi-square tests of independence, the chi-square test of goodness of fit and all this, the chi-square tests come out, all right? But in our module, the chi-square test is basically for testing the variance, the sample variance. Another thing would be relating to doing the two-sample t-test later on with the variances of the population unknown. And in order for the two-sample t-test to work, we have to have an additional assumption that the population variances are about the same. And so we will have a F test, okay? F distribution, okay? All right, it's not the word that is related to F, all right? So, we will have to do that, all right? So this is the first introduction, the chi-square distribution. You can ignore this, the gamma distribution. But when alpha equal to 1, this is our familiar exponential distribution. Okay, so we will ignore this. And again, not many of us, I think even if you come to the stat department, the faculty member ask them, suddenly you knock at the door and ask them to tell you the density function. I think many of us don't remember the density function. So this is rather not necessary. And you can Wikipedia it, all right? But this is the shape is interesting. There are many different kind of shape. This is called the degree of freedom. So the n here is the degree of freedom, all right? It has a variety of shape, chi-square distribution. When the degree of freedom is 1, this is the red color curve, corresponds to our exponential distribution, all right? So the chi-square distribution is not something, or the gamma distribution is not something that is, I mean, the gamma distribution is more general than the exponential distribution, all right? It gives you the flexibility. All right, so we will have this. It has a variety of shape. And you will see gradually, when the degree of freedom is larger and larger, it looks like bell curve too. So you will see, again, something to do with the central limit theorem. All right, we will relate to this a bit later. So the chi-square distribution, the value are always non-negative. All right, so this is in sharp contrast with normal distribution. Normal distribution takes values from -infinity to infinity. But of course, most of the time, it is sandwiched between plus or minus 3 sigma in the normal distribution. But in the chi-square distribution, it's always non-negative. So it won't take negative values. The chi-square distribution is a family of curves, each determined by the degrees of freedom of the distribution. We call it the degrees of freedom. It's basically a parameter. All the density functions have long right tail. Well, this is a little bit qualitative, okay? What is really meant by long is another thing. So I think you probably won't even need it. The expectation of a chi-square of n degrees of freedom is equal to n, and the variance is twice of it. This kind of property, I would admit sometimes I don't even remember it. Well, if I don't, I need to use it. I'll just Google it. All right. So I think the qualitative thing, these are too specific. So this is important to know. Is non-negative, and it is when the degrees of freedom is large, it is closer and closer to the normal curve. All right, and this. Of course, when you want to pin down the normal curve, you need the variance and the mean, and here you have to Google it and find out the mean and the variance. Okay, this is the most important thing that you probably need to know. If y1 is a chi-square distributed random variable, y2 is another one, y1 has degree of freedom n1, y2 has degree of freedom n2, and so on. An important assumption is they are independent. All right. If they are not independent, then the statement won't hold. Now we are interested in the sum of all the chi's or all the y. So two important conclusions. One is that it is still a chi-square. Second, to pin down a chi-square, you need to find out what is the degree of freedom. The degree of freedom is simply the sum of the degrees of freedoms of the individuals. All right. So sum of independent chi-square is still chi-square, and the degree of freedom of a sum of chi-square is the sum of the degrees of freedom. Okay. So if you decide to sort of remember certain things, this is the slide you need to remember. The previous slide is probably not too important. Okay. How does the chi-square come about? One of the things is the chi-square come from a normal distribution. So now, of course, we are not able to prove this. If you have a standard normal, the square of a standard normal is a chi-square of degree of freedom 1. So this is how it comes about. Now, if your x is normally distributed, but not necessarily standard normal, the thing is that you have to standardize it first. So this is x minus mu over sigma. The device here, change it to a standard normal. Then we are just using the previous statement. The square of this is still a chi-square. So this statement is actually coming from the earlier statement here. And then the third statement is also coming from the result of the second statement as well as the previous slide. Okay, let me explain. Xi minus mu over sigma will be a standard normal. All right. And now, if you have a standard normal, you square it according to the statement here. It will be a chi-square of degree of freedom 1. Okay. And now you are adding n of them. The previous slide says that if you add them up, it will still remains to be a chi-square. And the degree of freedom would be adding up the degree of freedom. And each one is degree of freedom 1. So as a result, y here, which is the sum of this guy, is a chi-square of n degrees of freedom. Okay. I would admit that this is rather coming too fast to you guys. Yeah, because we can't prove a number of things, and then some other statements follow the others. So, yeah. this is the part that I didn't like statistics when I first learned it. So I hope you won't repeat my mistake. All right. So the chi-square table consists values of chi-square. And now you have many tables for different n. You need a table for 1. You need a table for n equal to 2, and so on and so forth. To prove my point here, actually, this book is published in 1950 for binomial distribution. I don't know how many pages are there. Did it say? Oh, it's 410 pages. And this is rather boring. Okay. Let's say, okay, after the first maybe 50 page or 20 page explain, then everything is like this. All right. So, well, this is already it is already in soft copy. But in the past, you have to look for a hard copy. All right, so you borrow this book is this thick. All right, so yeah, so life is easier for you guys now. Okay, so you will need another table, but this is now better because n is taking the increment 1, 2, 3, 4, 5. So and also together with the fact that when n is large, it would be approximately normal. So say for n bigger than or equal to 30, then people don't tabulate it anymore. And so, yeah. Later on, I will show you, I have uploaded it. This is not done by me. Some of this table was actually produced. This is uploaded in the Luminous. So this is for n equal to 20. So whenever you come across a table, the most important thing is to read the caption of the table. So this is n equal to 20. The other important thing is this is here. Okay, this is measuring the upper tail probability. Now, suppose you are interested in computing the probability of a binomial 20, and then p is 0.3 equal to, let's say, 11. So you look at 11 here. But this, you have to do a little bit of work. Okay, so if you are looking at this, then you have to subtract these two numbers in order to get the point probability. So this is how we live our life, I mean, at that time, all right? So didn't get sympathy from you guys. So anyway, so this is this. Now, you have to be very careful when you are using a statistical table from books or from internet, because different people have different version. Here in our version, we think of it as alpha. We always measure things from the right upper right tail. It has a historical reason. First of all, NUS has been using statistical table that is produced by the UK, and they measured the area from the right-hand side. And another main reason is because in statistic hypothesis testing, it is usually this tail probability that is crucial to define the rejection region. So that is one reason. But when you are now calculating the probability, you have to be careful. You calculate everything from the right, all right? So if this is area alpha, so the unshaded area would be 1 minus alpha. And so in order to get that. Now in R, if you wanted to calculate the right upper tail, R has an option called lower dot tail equal to false. Okay, meaning that by default, R will calculate everything from the lower tail. But if you insist that this statement is false, then the R will calculate the upper tail instead. All right? Okay, we first define what is a sample variance. Now, there are two versions of sample variance. One, this is the version that we are using, 1 over n minus 1. In your calculator, probably at least during my time, you will have two buttons. One is 1 over n, and then the other button is 1 over n minus 1. Now, when n is rather large, it doesn't really matter much, all right? But when n is, say, 10, it might matter because it differs by 10%, all right? There are good reasons for n minus 1. There are also good reasons for 1 over n. That is why there are still two versions that are remaining. Another thing that you have to be careful when you're calculating standard deviation using R, you do not know whether R is using 1 over n minus 1 or 1 over n. So the best is to look at the manual, or you fit in a minus 1 and 1 and see what the result is. Okay, so anyway, so this is the key here, okay? In all our subsequent discussion, it is 1 over n minus 1. And this, of course, assumes that the sample size has to be at least 2, right? Otherwise, we are dividing by 0. Yes?
I was just wondering, so that sample variance, how is that different from the variance where we just said that sample variance is population variance over n?
Okay, so this is the favorite slides, 800 something, right? The slides that is the simulation part. The distribution in itself is rather difficult. So because we didn't really plot this. Now, for example, if you use this, if you were to repeat the simulation, what you should do for this case, you pick any two numbers, but now instead of finding the sample mean, you find out the sample variance. And this would be x1 minus x2 squared, because n is equal to 2. And so you will record this number, and you repeat this simulations, say 10,000 times. So you will have 10,000 numbers. Okay, and these 10,000 numbers, now you do a histogram, and so that would be the distribution of the sample variance for these situations. All right, so we didn't do that. I think in theory, I will do it maybe next time. I'm not very computing. So I've mentioned many times, I'm not being humble. It's not my trademark. Anyway, let me try it in my office first, and then I will show it to you. But basically, if you really want the distribution of the sample variance, you really have to basically repeat these calculations. Yeah. I mean, I'm quite sure this is a piece of cake for all of you. Okay, so I'm using 1 over n minus 1 in my averaging, and it can be shown, everything is high under here, it can be shown that the expectation of S squared equal to sigma squared. This is the reason why we use 1 over n minus 1. If we were to use n, 1 over n instead, the sample variance, if I were using 1 over n, it would work out to be n minus 1 over n. So I'm off a little bit on the average. Okay, so this is what we call unbiasedness. So on the average, the mean of your sample variance, that was the histogram that I was asking you to do, I mean the 10,000 times. And if you take the average of all these 10,000 numbers, it would give you the variance of the populations. All right? So this is the unbiasedness. The other version, 1 over n, is what we call maximum likelihood estimators. So there are good properties for 1 over n, and there are also good property for 1 over n minus 1. So it's not quite decided, all right? We shall instead consider the sampling distribution of this. Now, this is the crux here. You have to multiply this one by n minus 1. The reason is this. If you multiply this one by n minus 1, so there is no numerator anymore. And so this is how the argument goes. All right. So the sample variance, we have a square here. And 1 minus n minus 1, xi minus x bar square. Okay, so the next slide, the slide that I just show, would be something like this. All right, and over sigma square. Okay, so we are looking at this because we multiply this factor over. All right, and the sigma square is sort of like standardization. Okay. Okay, so we are looking at this. Now, they haven't told you what is this yet. The sampling distribution of the random variable, n minus 1 times the sample variance divided by the population variance. Okay, if I assume the individual measurement is from a normal populations, so this is here. So this is the table. I think we have something like this in this. Oh, by the way, now of course the table is not important, but it is important for a few minutes in your life maybe. In the exam, if you don't have a graphic calculator, we will be providing tables of this form, the form for the right distributions, and then put it at the end of the exam papers. And so you will be using the table. But I think if you have a graphic calculator, you can just simply give us the answer, all right? Of course, we won't set this kind of questions. We will have a little tweak, at least to make sure it's on the same level playing field, all right? Okay, this is the important conclusion. So this is the quantity that we are looking at. And this is this quantity. And this quantity is a chi-squared distribution. But now it is 1 degree of freedom less than its original sample size, n minus 1. If you compare this with the previous one, this one, it says its sample size, this is the degree of freedom n. But here we are subtracting the mu. We are not subtracting from the sample mean. So when we are subtracting this from the sample mean, we lose 1 degree of freedom. All right? Okay, so we lose 1 degree of freedom. But this is realistic because your mu is usually not available to you. And so all you need to do is to replace the mu in that previous slide by the sample mean. All right? And so as a result, you have to settle 1 degree less. Okay, and that is why we wanted to introduce the chi-square distribution, because now if we know the distribution here, we can answer probability statement about S square. Okay, this is the example here. Suppose 6 random samples are drawn from a normal distribution, n mu 4. Now, actually, we do not even need to know mu because the sample variance make no use of the mu. So we can keep the mu as unknown, all right? And variance of the population is 4. We are interested to find out this. Now this is actually, you may not realize, we are actually computing something like a critical region for hypothesis testing, but this is just one of the key steps. So we are interested in finding the C so that the right upper tail probability is only 5%, which we deem it as unlikely. All right, the 5% is small. Okay, anyway, to calculate this, we make use of this statement. All right, so this is where is the key. S squared is not known, so we cannot compute this directly. So we can do this. Now n equal to 6, so n minus 1 is 5. And then I have a s square, all right, as before. And then the sigma square is equal to 4. So I just substitute everything in, and so I have a chi-square of 5 degrees of freedom. Okay, so I can't calculate this directly, but if I rescale it as 5 over 4, then I can calculate this. Now here you have to use the table, or you use from the chi-square table, or use a graphic calculator, or use R, then you will have this number, 1107. So this whole thing is 11.07, so we can solve C back, and it is 8.86. All right. So this is actually from the table, or from Excel, or from R. All right. Okay. So this is what I was referring to. If you do not type in this in R, the default is always from the lower tail. But now you want upper tail. That means you want to basically suppress the default value, the default calculation. So the lower dot tail is equal to false. Okay, the t distribution. I think I need to steal some time from you guys, maybe another 5 minutes, because I'm a little bit behind than the other class. For a while, we were hoping to finish this, which is wishful, by the end of 12th week, but it's unlikely. So, so the bad news is probably we need to go into the 13th week. So let x1, xn be independently identically distributed with mean mu and variance sigma square. And so as a result, this is from what we have known before, previous result. So there are quite a number of things that you need to recall. And so as a result, if the xi's are normal, so we only need to use it here because we want to have this conclusion. All right? And so this standardization of the sample mean will be a standard normal. So this is provided this calculations is only meaningful when sigma, suppose I want to say something about mu, then this is the quantity that I want to involve mu, but I don't want the sigma to come in my way if sigma is unknown. If sigma is unknown, everything will be in terms of the unknown sigma, and so we can't do that. Okay, and when n is, now here, okay, the difference between this slide and the previous slide is this. The previous slide is making an assumption. Xi is normally distributed. But if you want to forego this assumption, the next slide is saying that then if we do not assume anything about Xi, then we have to borrow the strength from the central limit theorems, and so we need to assume n is large. So this is they are basically two different assumptions. In the first one, I do not require n to be large, but I now require the population is to be normally distributed. But here, I drop the assumption of the population to be normally distributed, but I need n to be large. And we can use our rule of thumb, when n is around 30 or above. Okay, so you note that this is approximately standard normal, okay? Whereas in the previous slide, it is exact, all right? Okay, but if we do not know sigma, not knowing sigma does not invalidate the results. However, we need a practical way to get around it. Now, not knowing sigma will not affect our conclusions of the previous two slides, but what it's trying to say in this slide is saying that some subsequent calculations we will have problem because all our answers will involve an unknown quantity, and so we can't calculate them. And so we need to estimate the standard deviation of the population from the sample itself. Okay, so this is what it is. All right. Now we can show that this is a sensible thing to do in the sense that because on the average it is equal to this, so we are not too far off by dropping the expectation. All right. Note that, however, sigma is a constant and s is random. It's a random variable. Substituting s for sigma will change the distribution of our statistics. The statistic was referring to here. All right. And now, since sigma is not known, I wanted to replace the unknown sigma by s, but now I change my distribution. Okay, and someone work it out. And the name of this publication is called Students' T-distribution. All right, so this is another form. So I will explain it first. Okay, the actual guy is William Gossett, and published a paper in 1908. And I think he was working for Guinness Beer Brewing Company, and the company forbids, without permission, to publish paper under your name while you're working for the company. So he used a pen name called Student, all right? So that is why it's called Students' T-test. It's actually a Gossett test. Now, this is stating it in a rather general manner, but we will specialize it. Okay, basically what it says is, let me highlight the different component. So you have this, and this is a normal distribution, standard normal. And then this is a U. U is a chi-square of degree of freedom n. And so now here you have to standardize it by dividing it by n. And you have to take the square root of this guy. Okay? And if this is the case, this guy is now T distributed of degree of freedom n. Okay? Okay, so you don't need to remember the probability density function. Once again, not many of us actually remember it, all right? If you wake me up anytime, I wouldn't be able to tell you the formula, all right? Not many of us remember the formula. Okay, so this is the, if you really need to pay attention, this is the one here. So let me repeat. The numerator is a standard normal. And then the denominator involves the square root of a quantity. The quantity is a chi-square of degree of freedom n. Normalize it by its own degree of freedom. So u over n here. And now you are not considering this, but you are considering the square root of this. Okay. And this is called a T-distribution of n degrees of freedom. So a T-distribution actually comes from a standard normal over the square root of a certain factor of a chi-square. All right? Okay. Okay, and now again, all the tables that we provide you will be a upper tail table. I think one of the tutorial questions, probably for next week, we have a very mundane questions, just asking you the probability. The question was trying to get you to use the table. But this is more like for preparing for the exam, just in case this kind of questions come up. All right. So we have this. In the table, the row corresponds to the degree of freedom, and then the column up here. So I think you can do that. And also, we are calculating the upper tail. So in R, we want to suppress this default option. And this. Okay. Again, you don't need to remember this. All right. The main thing is the mean is 0. All right. Okay. So by the way, this is an example when a t-distribution a distribution does not have a variance when n equal to 2, for example. Okay, this distribution, this t for degree of freedom 2 will not have a finite variance here. Okay. Okay, this is not crucial, but basically it's saying that the graph might help. So if you plot the density function of the t-distribution, first of all, the t-distribution is symmetric at 0. All right, it's the same as the normal. And then when the green color is the degree of freedom 3, and then the black one, the blue one is the standard normal, and then the red one is the degree of freedom 8. So you will see the degree of freedom is small. It has a factor tail. So if you want 5% of the green color, and if you mistaken it to be the blue color, which is the normal, then you are underestimating the area. All right, so that is why you need a corrections. But when the degree of freedom is getting a bit bigger, 8, you can see the red curve is now lowering down, or at least on the right, the tail part. So it's pressing down, it's getting closer and closer to the blue color, which is if you use normal distribution. So this is the contribution of a student publication, is to make corrections of this, because if the degree of freedom is small, the upper tail is much larger than that of the normal. So if you use normal as your guide, you will grossly underestimate this. Okay, so maybe I'll stop here. And I will relate this back to our sample variance. Okay, so
Like, why for this one, right? Why do we need to do the continuity correction?
oh, because the original thing is also a discrete.